Okay, let's continue our discussion of muscles, specifically with a focus on skeletal muscle fibers. Once again, a skeletal muscle fiber is the same thing as a skeletal muscle cell. And what we're looking at right here is the sarcomere. Once again, the sarcomere is the distance between the two Z discs. These black squiggly lines are the Z discs. We see the thick filament composed of myosin molecules. We see the thin filament composed of actin molecules. To be very clear, I only have one strand of F-actin. We have previously talked about the thin filament composed of two strands of F-actin molecules, but for simplicity and time, I've just drawn one strand, and it's quite a short strand on each side. The space between two adjacent thin filaments, the space between here and here, is known as the H zone. And recall that when the muscle contracts or shortens, that H zone diminishes in size or in width. And the contraction or the movement of those thin filaments creates the tension or force required to do work. Here in the middle is reflecting what's known as the optimal length tension relationship, the optimal length tension relationship. That is to say, we have the optimal length tension relationship when all the available cross bridges are formed. So we see only 4 myosin heads on each side and on top and bottom, but they're all bound to the thin filament, and that's going to allow a greater force of contraction of the muscle fiber because there are more myosin heads engaged. Another way to look at this is the H zone. There is an optimal width to the H zone as well, which is certainly correlated to the number of cross bridges formed. If we look at the top one right here, this is when a muscle fiber has been excessively stretched. This is not optimal because we only have cross bridges formed right here. Now, granted, there's a super large H zone, so if for some reason all those myosin heads could grab the thin filament, it would generate a great deal of force or tension as that H zone is diminished. But it's incapable of doing so because there are a number of myosin heads that aren't even engaged with the thin filament. So this is overstretched. And what we're talking about here with the optimal length tension relationship immediately prior to the beginning of contraction. So if we look here, the muscle can be slightly contracted potentially right before it contracts again. And if it's too short, too contracted, where the thin filaments are overlapping right here, there's no diminishment that can happen of that H zone because it's diminished already as far as it can possibly go. So the length tension relationship has everything to do, one, with the width of the H zone, but more importantly, the number of cross bridge formations that have been created. Now, while we're talking about muscle contraction, let's make mention of the sources of ATP for muscle contraction. They are just some residual ATP in muscle, substrate level phosphorylation, glycolysis, and oxidative phosphorylation. I have oxidative phosphorylation, the fourth point right here, because this is going to require oxygen. ATP, there's going to be some residual ATP in muscle fibers that is going to be used up probably within a second, if not less. There's going to be substrate level phosphorylation. We've talked about that previously. That's borrowing or lending a phosphate from one substrate to the other. The other is always going to be ADP, adenosine diphosphate. If we can add a phosphate to that, it becomes ATP, and that becomes a source of energy for our working muscle. The substrate that lends it is more likely than not going to be a creatine phosphate. Creatine phosphate will lend a phosphate to ADP to create ATP. Then there is glycolysis. Glycolysis, once again, is the first phase or stage of the entire process of cellular respiration. It's somewhat of a misnomer. That is to say, cellular respiration is a bit of a misnomer because with regards to glycolysis, because glycolysis does not require oxygen. Respiration is intimating the use of oxygen. Now, to be clear, glycolysis does still happen in the presence of oxygen, but it can happen and does happen in the absence of oxygen. And that ATP is produced very quickly, but without oxygen, the pyruvate that's created during glycolysis is going to proceed into lactic acid fermentation, and that potentially could lead to some fatigue in the muscle. So these first three would be enough to sustain one for up to maybe 1 minute. After that, they've run out of ATP. Oxidative phosphorylation, once again, is using the mitochondria, specifically the electron transport chain, the ATP synthase, the proton motive force, chemiosmosis, everything we've talked about with regards to oxidative phosphorylation and the electron transport chain. So this requires oxygen. It also requires a lot more time, but it produces a lot more ATP than glycolysis, the substrate level oxidative phosphorylation, or the residual ATP left in the cell. So oxidative phosphorylation is going to produce a lot more ATP, but it's going to take a lot longer to do so. So we've been talking about tension, which is the creation of force by a muscle fiber, but let's talk about the mechanical and electrical events that actually allow for tension and force to be generated. So we have a term known as a twitch. This blue line right here is representing a twitch. And a twitch is nothing more than one contraction relaxation cycle. To be clear, this is not showing electrical activity. This is not an action potential. It's not a graded potential. It's just demonstrating or representing the mechanical activity of the muscle fiber, contracting and relaxing. One twitch is one cycle of contraction and relaxation. To be clear, we cannot have a twitch, we cannot have muscle shortening without some sort of electrical activity. And as we demonstrated in a previous video, that electrical activity is facilitated by a somatic motor neuron releasing acetylcholine, binding to nicotinic channels to depolarize the cell, causing a conformational change to the DHP receptor, opening up the sarcoplasmic reticulum, allowing calcium to leave the sarcoplasmic reticulum, binding to troponin, moving tropomyosin out of the way, and boom, we get muscle contraction. But that electrical activity, once again, is facilitating a twitch or causing a twitch. One thing to note, this action potential right here takes about 1 to 2 milliseconds. The twitch is variable between 7 to 70 milliseconds, depending on if we're a fast twitch muscle or a slow twitch muscle. But it's super, super fast. As a matter of fact, but the action potential is super fast in relation to the twitch. There's actually a delay between when depolarization occurs in the muscle fiber and when it actually begins to contract. That delay is known as the latent period. But we have an action potential causing a twitch. Now, if we look here, what I'm trying to demonstrate here is we can have multiple action potentials before that twitch even starts relaxing. So we have an action potential here, and just as that is starting to relax, the somatic motor neuron fires again, depolarizes the muscle fiber, and keeps the sarcoplasmic reticulum open, or opens it back up just after it is closed. So the key to this is making calcium available. So the more times it fires, the more calcium is going to be available to troponin to move tropomyosin out of the way of the thin filaments. So what we get here is what's known as summation, repeated electrical stimuli to the muscle fiber, which will keep calcium available to troponin, keep the gate of the sarcoplasmic reticulum open. And we can see right here that this is firing very rapidly right here. As a matter of fact, these vertical lines are just showing action potentials that are happening very rapidly. So I'm not showing the delineation between the depolarization and repolarization. It's just straight up and down. So what happens here is the muscle starts to relax, and then the somatic motor neuron fires again. Starts to relax, somatic motor neuron fires again. This is not only going to cause or diminish the time the muscle relaxes, it's going to increase the force of contraction up to a point. And muscles can only generate a maximum force. So it gets up to here, and if the somatic motor neuron is firing enough, if summation is occurring, just adding the rapid, frequent action potentials together, it's going to keep the sarcoplasmic reticulum open and keep this up here to sustain muscle contraction. Right here, we have what's known as tetanus, and that's sustained muscle contraction without any relaxation. Here is what's known as incomplete tetanus or unfused tetanus because it's relaxing a little bit, but tetanus is sustained muscle contraction due to summation. Summation is what's happening to the electrical activity of the muscle fiber. Tetanus is the mechanical activity. So it's important to differentiate between the mechanical activity and the electrical activity. If we look over here, what I'm trying to show is a process known as recruitment. Recruitment is bringing on more motor units to increase the force of contraction of the muscle. So what I'm showing right here is a muscle known as the biceps brachii. It's not a great drawing. That is to say, I have a group of cells right here and a group of cells right here that I'm trying to demonstrate that they're both part of the biceps brachii. Muscles have thousands upon tens of thousands of cells. To be clear, I'm just drawing 6 cells, which are skeletal muscle fibers. These 6 blue ones and these 6 green ones right here. And the reason why this picture is not totally accurate is these green ones are probably within the triceps brachii rather than the biceps brachii. But please don't worry about that detail right now. Let's just assume that all 6 of these muscle fibers are part of the same muscle. So let's say the biceps brachii. For each group of cells, we have a somatic motor neuron. So we have a somatic motor neuron right here, innervating these 3 cells. We have another somatic motor neuron right here, innervating these 3 cells. One somatic motor neuron and the skeletal muscle fibers it innervates is providing nervous stimuli. One somatic motor neuron and the muscle cells it innervates is what's known as a motor unit. Once again, a motor unit is just one somatic motor neuron and multiple muscle fibers. It could be thousands of muscle fibers, even though I just have 3 drawn right here. So when a muscle starts to fire, depending on how big that entity is that's trying to be moved by some tension or force, let's say an expo marker, it doesn't take much for me to pick up or do curls with this expo marker. So I may only need one motor unit, one somatic motor neuron, and in this case, the 3 skeletal muscle fibers. This 3 skeletal muscle fibers probably is unrealistic unless for the very fine-tuned muscles, say for the eye, but tend to be thousands of muscle fibers per motor unit. But now if I'm picking up a dumbbell, let's say a 30-pound dumbbell, which I'm not sure I could curl, but if I could, I need to recruit more motor units. I need to bring on more motor units to generate more force. So if I then have this somatic motor neuron firing and that somatic motor neuron firing, we're bringing on the activity of more muscle fibers. And that is known as recruitment. So how do we increase tension or force in a muscle? One is the length-tension relationship that we talked about previously. That is to say, the optimal length-tension relationship where all the cross bridges are formed that potentially could be formed, and there's a specific distance of the H zone. To have the optimal length-tension relationship is one way to increase tension or force. Recruitment is another way. That is to say, bringing on more motor units. The third way is summation, and that's what we see right here, creating tetanus. And the big premise with summation is it keeps calcium available. If calcium is available from the sarcoplasmic reticulum, the ryanodine channel continues to stay open or opens very frequently. There's going to be more calcium available, binding to troponin, keeping tropomyosin out of the way, and allowing that thick filament to continually grab the thin filament and shorten that muscle fiber. Let's talk about the 2 types of muscle fibers there are specific to skeletal muscle: slow twitch muscle fibers and fast twitch muscle fibers. Slow twitch are also known as type 1, fast twitch are known as type 2, and full disclosure, there is an intermediate one that's somewhat between slow twitch and fast twitch, but we're going to just keep this at slow twitch and fast twitch. In short, fast twitch muscles will engage in contraction and relaxation much more rapidly than slow twitch. Once again, a twitch is a contraction relaxation cycle. A twitch within a fast twitch or a type 2 muscle is going to be as quick as 7 milliseconds, whereas slow twitch is as long as 7 milliseconds. A lot of this has to do with the ATP ACEs that we have within skeletal muscle. To be clear, we have the myosin ATP ACE, the myosin head. When it moves, that's actually an enzyme that hydrolyzes ATP. That's why we refer to it as the myosin ATP ACE in addition to the myosin head. So it has mechanical purposes, that is to shorten muscle fiber, but it also hydrolyzes ATP. There's also the calcium pump, which is pumping calcium back into the sarcoplasmic reticulum. And anytime we use the word pump, we can also replace that term with an ATP ACE. So a calcium pump is a calcium ATP ACE. And the myosin ATP ACE and the calcium ATP ACE hydrolyze ATP, engage in the metabolic activity of breaking down ATP much more rapidly than happens in type 1 skeletal muscle fibers. And that's what allows them to be much faster in their activity. Also, what allows them to be much faster is that type 2 muscles engage in glycolysis. That is to say, they're producing ATP without oxygen. That happens very fast. When we're using oxygen during oxidative phosphorylation, that happens with type 1 skeletal muscles, that happens longer. As we previously said, that produces a lot more ATP, but it's much slower. Slow twitch muscles have a smaller diameter, and fast twitch muscles have a larger diameter. Hence, if you ever slow twitch, we think of maybe sprinters or bodybuilders with these big, thick muscles versus long distance runners who tend to be long and lean and have small diameter slow twitch muscles. The slow twitch muscles or type 1 muscles are dark. That is to say, the meat is dark. If you're eating chicken or turkey, you probably understand that there's dark meat and white meat. The slow twitch is the dark meat because it's loaded with mitochondria, capillaries, and myoglobin. Myoglobin binds oxygen. It's a storage form of oxygen within skeletal muscle. Capillaries carry oxygen-rich blood, and the mitochondria produce ATP. So all of these are going to impart the darker hue to type 1 slow twitch muscles. And that's it for our skeletal muscle fibers.